I request to all the participants to kindly keep yourself mute. Tapan sir, if you are ready, can we start the webinar?
Yeah, sure. I'm ready. So do you want me to share the screen first, or I can do that later?
No, sir, we'll just go for introduction first, and later you can just have your presentation.
Sure.
A kind request to all the participants, kindly keep yourself mute during the presentation. If you got any like questions or queries, keep it at the end. And I request our project coordinator of Regional Science Center, MMK Balaji sir, to kindly take over the program. Sir, you are not audible, sir. Unmute.
Yeah. Now it is okay?
Yes, sir.
Audible?
Yes, sir, you are audible, sir.
So, good evening, everyone. And today we are here to celebrate the International Science Center and Science Museum Day. And Regional Science Center is celebrating this by organizing a Nobel lecture series. And we all know that every year the Nobel Prize is awarded in 5 disciplines. And these 5 disciplines like physics, chemistry, medicine or physiology, peace, and economics. So, when we know that Nobel Prize is named after the great scientist Alfred Nobel, who is the inventor of the dynamite. And in his will in 1895, though he invented the dynamite, but the purpose of using the dynamite was not as per his wish or as per his thought, because dynamites normally we use for destruction only. So what he thought is whatever the money he had earned from his invention, he decided to give it to the scientist, great scientist who is doing innovations or great discoveries in the field of science that will help mankind for their survival. So in his will, he clearly mentioned that the entire assets, whatever he has at that particular time, will be utilized for giving these Nobel Prizes. And the first Nobel Prize was started in 1901, and it was awarded to Rontgen, who has discovered the X-rays. And since then, more than 121 years, we are giving these, means the Nobel Foundation, the Royal Swedish Academy. The Royal Swedish Academy is giving these Nobel Prizes. So, and this year in 2021 also, we know that in physics particularly, 3 scientists, they got Nobel Prize for their work. Dr. Manabe and Dr. Hasselmann has won the Nobel Prize for the physical modeling of Earth's climate, quantifying variability and reliability, predicting global warming. And again, one more person has shared the Nobel Prize, Dr. Parisi, for the discovery of the disorder and fluctuations in physical systems from atomic level to planetary scales. So, this is a brief information about the Nobel Prize winners in physics for the year 2021. And to know more about this, today we are here with us Dr. Adhyapak, who is working as assistant professor in ISER Tirupati. And some brief introduction, I will give some brief introduction about Dr. Adhyapak. He did his MSc from IIT Guwahati and PhD from IIT Bangalore. After that, he completed 2 postdoctoral fellowships at the Technical University Berlin and Johannes Gutenberg University Mainz, respectively. Subsequently, for a short period, he has worked at Max Planck Institute for Polymer Research, Mainz, and then in 2019, he has joined the current position at ICER Tirupati. And he is interested in broad research areas of active matter, non-equilibrium statistical physics, driven soft matter, and biological systems. And his associate group works in analytical and numerical methods to study the above systems at the single particle level as well as in the limit of large length and time scales, where the systems comprise enormous number of particles. Additionally, in suitable situations, his team also employ methods that bridge these two separate realms. And to know more about his research work and more about the Nobel Prize winners and the topics which give or which created the 3 scientists who won the Nobel Prize, we are here to listen from Dr. Tapan Chandra Adhyapak. Sir, please take over and continue.
Yeah, thank you for the kind introduction. Let me share my screen first. Hi. Yeah, sorry. So I just when I started, I lost power. So can you, see my screen as of now?
No, sir. We're not able to see your presentation.
Yeah, isn't this? But this is the other side. Visible now or not yet?
Not yet, sir.
Okay, is it now visible?
No, sir. It's not yet. Yeah, now, yes. Yeah, now it's visible.
Okay, great. Okay, great. Just I want to confirm. So, are you able to see my cursor?
Yes, sir.
Okay, great. Thanks a lot. Okay. Again, thanks, Dr. Balaji, for giving the kind introduction and also for explaining what the Nobel Prize is about. And I'll be talking about the Nobel Prize in Physics in this year, 2021 specifically. And this title has 3 keywords: complexity, disorder, and fluctuations. And this year's Nobel Prize is about these 3 keywords. So I have quoted some remarks directly from the press release that is released by the Nobel Committee. So this year's Nobel Prize was actually awarded for groundbreaking contributions to our understanding of complex physical systems. This is the reason for the Nobel Prize in Physics this year. So the total Nobel Prize, there is a prize money, a huge prize money. More than the prize money, it's actually this is the highest prize that one can think of in scientific field. It is so prestigious, and once people get it, people easily become legends. So, but this year's prize money, as well as the whole share of the award, is divided into these 3 persons, and they are divided unequally. So, half of the prize goes to Giorgio Parisi, and the other half is divided equally between Shiguro Manabe and Klaus Hasselmann. And the reason for the awards are also taken from the same press release. So Parisi was given the award for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales, as also mentioned by Dr. Balaji. Similarly, the other two gentlemen, they were given the award for the physical modeling of Earth's climate, quantifying variability, and reliably predicting global warming. Okay, so these are the exact words. And then in my talk, I'm going to, I'm trying to explain what are these prizes for. And seemingly at first you can see that, these two topics are very unrelated topics. However, the Nobel Prize, the rule of Nobel Prize is that when you divide the prize among different people, it should not be for totally different works. So somehow these works are actually related, and how, then I'll explain. I'll try to explain at the end. And before that, so I can highlight. So these three words that also came up in the press release. Okay, complex, disorder, and fluctuations. So complex physical system is actually this example is there. In this example, we have this disorder and fluctuations, and we'll talk about what is the connection between this. So my research area is broadly, not exactly, but broadly related to this. But still, this work is very, very highly mathematical. It's very mathematical work. The foundation is very mathematical. The implications, the results were very, very broad. They are used in various different fields. But to understand it, we need lots of mathematics. However, I was told that in the audience there's high school students and +2 level students. So what I will do, I'll skip all the mathematics. Okay. Only show some schematics, and as far as possible, I'll avoid mathematics, of course. And let's see how it goes. And since this is from my field is closely related, so I would explain this work first in an elaborate manner, and then at the end we'll try to touch upon this topic as well. Okay, so this is the plan of the talk. So let's go ahead. So first, about so who won the half of the prize? And as you can see, he was before. His Nobel work was done around 1979. Before that, he was working on very different problems. Not only problems, the fields are very, very different. Okay, these are like particle physics, string theory, quantum gravity. And suddenly, he jumped onto this problem, spin glass, on which the work on which won the Nobel Prize for him. And the result of that work percolated in other areas like brain studies, neural networks, optimization problems in networks. And he is also known for this famous, very, very famous equation which carries his name, Parisian-Jain equation, that is also applied in various fields. So you can see that there is a big jump from here to there. And now at the end, he has done another jump, which is like one of my favorite jumps. Okay, I'll tell you why. So let's go ahead. So as I said, the work is really mathematical. So I'll try to only kind of give the main summary. Okay, thinking that high school students and +2 level students are also here. Okay, so here is Paris's Nobel winning work. So as I said here, the work was originally done in spin glasses, but later it became far-reaching. The ideas percolated to other fields. So what is the problem actually? What was done? So imagine that this is a liquid or fluid, okay, liquid or gas. Okay, so you can imagine that to be a collection of balls confined in a box. So in a liquid, if temperature is high, these balls would be kind of randomly moving in all directions, randomly. In a fluid, the balls will be like molecules of liquid. So they are randomly moving at high temperature. But if you reduce the temperature of this system, or you pressurize, you give pressure, more and more pressure to the system, so what will happen? So if you do the change in slowly, okay, so if you change the temperature slowly, for example, these molecules will actually start to arrange in a regular manner like this. Okay, this is called a lattice. So it's a regularly ordered collection of points. So that is what it is happening when you do the change slowly. And this is actually what we know as solid. So here it was liquid and it becomes solid here. But the same change, if you do fast, okay, if you do the same change fast, then what happens that the system does not reach a regular configuration. It's still, configuration is quite random like here, but something amazing happens in the sense that if you lower the temperature further down, no change will happen. So as if the system is stuck here. Okay. So here, for example, it is random, but if you reduce the temperature, something will happen. I mean, so the molecule will start arranging some other way. Here, molecules are random, but if you reduce the temperature further, no change will occur. So this is some kind of puzzle at that time. What is more puzzling was that suppose you do the experiment again. Again, you start with the system. Again, make the change fast. You repeat the experiment. It turns out that the state that you reach here is again disordered like here. Okay. However, this state is different from that state. So here, if you do it slowly, the state that you would have reached, it will be always same, no matter how many repetitions you do. But here you get different states. So these are examples of structural glass. The glass that we know, so this is like the glass that is that usual tumblers are made up of, for example. Okay, the same glass that looks like this. Okay, so I mean, there are many puzzling questions regarding these systems. So I just list the most easily understood two of them. So first of all, we can ask why different repetitions yield different patterns. Okay, this is very easy to ask questions, but it is very difficult to answer theoretically. And second, why the glasses are rigid? I mean, we know that solid are rigid. We ask the question why glasses are rigid, and then we'll come to these questions again. Okay, so why this is actually a puzzle, I'll explain. But before that, I want to mention, I mean, P.W. Anderson's quotation. I mean, so Anderson himself won Nobel Prize before Parisi did, and he quoted that these questions are one of the deepest and most interesting unresolved problems in solid state theory. Okay, this is such a fascinating system. So we understood some part. I mean, let us understand why. I mean, what is the problem actually? Why? I mean, so this is a very difficult system to study. This is called structural glass, as I said. But there is another system which is called the spin glass, on which Parisi worked. So this is actually a metal alloy. So they are mostly it's copper. So all these blue dots are copper atoms. And in between, iron atoms are inserted. And these iron atoms go and sit at random positions. Okay, they are not ordered. These red dots are the iron positions. Okay. Now, each of these iron, they carry a tiny magnet. Okay, like the one that all of us know. So these arrows shows the tiny magnets. Okay, so like north and south pole directions. Okay. So this is the spin glass, but before we understand spin glass, we have to understand what these spins are doing, interacting among each other. So let us, these spins here, they are randomly located, as I said, because these red molecules are randomly distributed. To understand that system, let us see a system where we have these molecule arrows that are placed at a regular positions like this one. Okay, and consider two of these arrows like these two. Usually their interactions are such that they want to align align along each other. So if this is parallel, pointing along one direction, it tries to make the other also point along the same direction. Sometimes it can be opposite alignment. Okay, like this one. So these are the interactions that every player is having. So now, if you have such arrows, so we call it spin, by the way. The technical term is spin. Okay. So if the spin means nothing but these tiny magnets. So if you have these spins, and if we have at high temperature, this spin will fluctuate a lot. and they will randomly align among each other. And this is very similar to the random position of the liquid molecules. Okay, this is the similarity. However, if you lower the temperature, such kind of interactions that the spins want to be parallel along each other, the interactions will make them align along each other when you lower the temperature. Okay, so these spins are all aligned along each other. Such a state is actually similar to the ordered state that we talked about for the other type of glass. Okay, so but what is more in this case is something called frustration. What is that? So suppose there is a triangle here. So in one of the vertices of the triangle, I place a spin, and that is up. In the next vertex, I have to put another spin, and let's say that the spin try to be anti-aligned. They want to be opposite to each other. Then of course this spin will be down because that was up. Now let us try to put the third spin here on the third vertex. Again, we demand the same thing, that they want to anti-parallel, and they want to be anti-parallel. But now the third spin will point in which direction? If it is upwards, then it is anti-parallel with this one, but these two are parallel. If it is downwards, for example, then these two are anti-parallel, but this is parallel. So neither of these configurations is actually happy. Okay, so that leads to a frustration in the system. So the spins as a whole, if you leave them there, they don't know where to which way to point. So that is called frustration. And this frustration actually, so here these points were arranged in square lattices. So if you arrange these spins in triangular lattices like this, then this frustration is really huge, okay, in these kinds of systems. Now these are already there in the ordered spins. These are all ordered spins. But what about our system, where the spins are now kind of randomly distributed? Their distances are different. You can see that this is closely situated. These spins are situated further apart. That means that the effect they have on one another is different, because these two will be strongly affected because they are closer. These two will be weakly affected because they are further apart. The strength of the interaction, so whether strong or weak, we denote it by something called Z. Okay. Now you can see that this Z is defined for different pairs because the distances are different, right? This is called the disorder in the system. So the Z's are random. And like in the previous case, in this case, we had frustration. This disorder leads to frustration and much more, actually. Not only frustration, but there are various other things. And one of the fascinating results is that if you lower the temperature, there can be a state of the spin where the spins are random, like here. So the spins are randomly oriented, not particularly oriented in one direction. However, they are frozen. They are not vibrating anymore. I mean, they are slightly vibrating, but they are kind of, it's very hard to change the orientation by much. Okay, so this state is called spin glass. This is what Parisi worked on. And I'll explain more what are the more deep questions, okay, about this. But this system, as I said, was very analogous to the glassy systems, right, that we encountered earlier. This system, this system, analogous to that system. So however, the spin glass system, they carry similar questions that the structural glass has, but it's a new platform, it's a new system where you can work with the mathematics a little easier. Okay. So that's why people started to work on this to understand what's going on in glass. So that was the kind of introduction, but let me give some more intuition. I mean, why the puzzles are actually really puzzles. So take for this system of spins, at high temperature, as I said, these spins will be randomly oriented, and you lower the temperature because they are on a regular lattice, all of them will be aligned, like here. Okay. So, but the alignment is also fulfilled here. So if all of them are actually vertically aligned, then also mutually they are aligned. If they are also aligned in other way, this here also they are mutually aligned. So all these have the same happiness. So when the spins are sitting next to each other, they will be happy, equally happy in all three configurations. Okay. In fact, there are infinitely many configurations like that. So all you need to do is to make them parallel to each other. Which direction they are pointing doesn't matter. So we call that there is a rotational symmetry, because you can rotate. So because you can say that this state is rotated to get that state, and this state is rotated to get this state, and so on. So there is, and because all of them have the same energy or same happiness, we call that there is a rotational symmetry. But the moment the system picks up one of them, we call that the symmetry is broken. Okay. Now, in this kind of system, what you can do, you can apply a field like the Earth's magnetic field. Okay. So Earth's magnetic field try to align magnets, right? So similarly, you can apply a magnetic field to align these spins, and you can actually choose which one of these states you want to go into. This field, it turns out that is very important both theoretically and experimentally. So this field can be applied to do the mathematics of the system easily, to break the symmetry easily, both theoretically, and also you can break the symmetry experimentally as well easily. So it's very essential to have this field actually. Okay. However, let us come back to the spin system. So here the spins were organized, but here you can see that they're disordered again. And at large high temperature, these are still fluctuating a lot. Okay. If you lower this temperature, as I said, they come to a situation where the spins are frozen. They're random, but they're still frozen. So the fluctuations have reduced a lot. So this is the spin glass. But now you see that there is no symmetry that is broken. There is no symmetry here. So there was a symmetry there, but there is no symmetry here. So the question arises, what symmetry is broken? Okay. And what kind of field is there which can create such a frozen system? Okay, why the system is frozen, we don't know. I mean, so and then how? So this is a theoretical challenge. I mean, so because we don't have that such a systematic field, it's very difficult to understand or tackle this system. This is one of the greatest problems here. Another problem is here. I mean, this is a problem of understanding. So consider the regular lattice points, and suppose you rotate the central spin a little bit like that. Immediately, all the neighbors will be unhappy because they are not parallel with this one, right? So the neighbors will become unhappy, and they'll try, all of them together will try to make the spin again aligned to the earlier position. Okay, this is the reason of stability or rigidity in terms of structural glass. So if you try to change the state a little bit, this system offers lots of resistance. And that is because you can see that it is already in an ordered state. So you have broken some symmetry, right? What is happening here in this spin glass? If you try to rotate one of the spin, the neighbors, all the neighbors are neither happy nor unhappy because they are not anyway aligned, because seemingly there is no broken symmetry. So then how this system is stable or frozen? Okay, you can see at just level of this picture that there are so many puzzles that is hard to tackle. So one more difficulty level is here. Okay, so suppose this is your sample, the spin glass material, the alloy, and you look at a tiny portion in the alloy, just magnify it, and you will see this the spins that I have already shown you. And we already talked about the disorderedness, the random positions of the spins. Okay, this is called disorder. But suppose you keep the disorder same, because of the finite temperature, these spins will again fluctuate. So here the positions of the spins are same, but the orientations are different. Okay, so at the same position, the spins are fluctuating. This is called fluctuation. Okay, this is disorder. Disorder is the random positions, and in the same position for the same J's, the change in orientations are the fluctuations. So we know how to deal with fluctuations. So suppose we stick to one kind of disorder, like for example this part. Okay, so this part. So we know how to calculate the disorder fluctuations. That is by help of statistical mechanics. So what we do, we calculate something called a free energy. Okay, and this is like a magic property of the system. Don't worry about the mathematics here. It's a magic property of the system. If you are able to calculate that, all the properties of the system you can calculate. Okay, you can calculate from there. So that's what you can do it here also for this sample. Now the problem is that the free energy that you calculate in this way will depend on the disorder, because you just fix the disorder here, right? That's what you can do. So the problem is that the free energy depends on the disorder, that is disease. That means that the derived properties will be sample specific. So the property will be here be different. And if you go to a different point, for example, here, the disorder will be quite different. Okay, the locations of the spins are very different days. So that means that the derivation that you did will be only true for this part, but will fail to explain this part. But this is something nonsense. Okay, this is not true, cannot be true. The reason is that although I said that you get only one disorder here, but no matter how closely you look at, so I mean, our instruments are always have a limitation. So even though we go to the highest resolution, we'll be left with many this kind of disorder. So we have to average out the disorder. And if we do that, I mean, so the material property should not depend upon position to position. The entire material property has the average property, right? So this cannot be true. I mean, this method doesn't work. And this is the method that was there before Parisi and Anderson, they came into this picture. Now let us go to the next level. Let us try to work it out. Okay, these are the kind of problems that was persisting in the system. So let us try to work it out. So first of all, we had to deal with how to include disorder. Okay, how to make the properties averaged over the entire sample, so that we get a unique property for the entire system. The first idea came from Anderson, okay, in 1975, and he derived something called replica trick. Okay, so the trick is that the same property, the magic property, free energy, we have to average. So this is the symbol for average, average over disorder. Okay, so in order to do that, we have to average this quantity. And this is the mathematically challenging part. It's a really hard. I mean, so it's very simplified way I showed, but there are lots of integrations, differentiation included there. Okay, so this was very difficult, but there was a mathematical trick that was used, and that trick, don't worry about the mathematics, you don't have to understand that fully. But one thing I want to point out, there is an n sitting there. Okay, so this trick along with this n suggested something amazing. That is this: that suppose you have a system. All you have to do is to imagine n copies of the same system. And when you imagine n copies, you have to imagine also the fluctuations of the spins and all that, okay? But you have to do that for a given set of J's. Okay, is there any question? So I'm not, I hear noise in between. So are you able to hear me? Can somebody confirm?
Yes, sir. Yes.
Okay, great. So yeah, so how to deal with disorder? You have to imagine n copies of the same system along with their fluctuations for a given set of J's for a given disorder, and then you average over disorder. This is the trick. I am not going into the detail of the mathematics, but this is the trick. And pictorially, each of these copies is called a replica. And this is the picture. Okay, so you consider one particular disorder, so one particular random locations, and this is one set of orientations of the particle. So this is one copy of the system. However, you have to consider also the fluctuations. So in the same locations, you can have different orientations. So you consider all possible fluctuations. And together, all this set will be called one replica. And when you consider these fluctuations, this system and that state, this is one state of the system, this is another state, you also have to consider the statistical weightage. So the probability that the system is in this state, you have to consider, and the probability that the system is this state, you also have to consider. And these probabilities will be different, okay, for different states. And once you have this certain state, this is called one replica, and then you consider another replica 2, just copy it, okay, and so on. So in that way, you consider n replicas of the system, and then you can do the mathematics and then do the averaging, and you can finally calculate the free energy. That is the trick offered by Anderson, but there are certain problems there. So one problem is that, so if you consider the replica 1, so at high temperature, these spins are really fluctuating, right? So all these different states are accessible from one another. So it doesn't matter if the system starts here or starts there. The system will go from here to there to here, and then so to the other things, other states as well. So configurations are accessible from one another. Therefore, the weightage in all replicas, I mean, so because this again is there just a copy of this replica. So this configuration is, for example, same as this configuration. So the weightage here is same as the weightage there. The probability of these two configurations are same. Similarly, these two configurations are same, and so on. In that sense, these two replicas are exactly same at high temperatures. But something amazing happens at low temperature. Okay, in this state, because of this, because the replicas are same, they are called symmetric replicas. Okay, but if you lower the temperature, already we saw that the system can get stuck in frozen configuration. Right. For example, this configuration can be frozen. So if the system starts from here, it cannot go to that state because it is frozen. Then in that case, probability of this state will go really down. Right. So similarly, if you come here and then if you say that your system started here, then the probability here will be high. And then you cannot go to the other system because these are frozen. That means that the same configuration, this one and that one, in different replica might have very different weightages, probabilities of occurrence. And that is called replica symmetry breaking. Okay, so this is you need at low temperature, especially for spin classes. Now, although all these concepts existed, and these were the attempts made before Parisi. Okay, for example, Anderson first formulated the replica trick. He understood something, but not fully. But then the problem was that, I mean, Sherrington and Kirkpatrick, they revealed that their work has an unresolved paradox. Okay. And this paradox we tried to solve later on, resolved. The paradox were resolved, but then the solutions were not so stable. I mean, so mathematical solutions were not realistic. Okay. You see all sorts of problems arises. Okay. Although things were kind of getting more and more clear, but the problems are getting more and more complex. Then some people, two of these gentlemen came and then showed that all these solutions had a big flaw, that they actually assume replica symmetry. That means that they were all this state. I mean, so they were all at high temperature. They are not really in the temperature where you get spin. Spin glass. So then afterwards, people try to break the symmetry, but those were unsuccessful attempts. That is the state from Anderson's work to the Parisi's work. And then look at these people. I mean, so how famous these people were. I mean, so I just noted these three gentlemen in red. These are people who actually Thales and Anderson both received Nobel Prize. Okay, so it was. I just gave you only a handful of examples. There are many other people who were working on it, and then people were not trying to. People did not make a breakthrough, and then came Parisi. So he made a breakthrough in 1979, and he solved the problem of replica symmetry breaking. Okay, this is the thing, and then again, this is a very highly mathematical thing. I'll try to explain in a pictorial manner. Okay, let's see. So we talked about this replica, right? So the same replica exists. Okay. Okay. Just 1 second. I'm trying to switch to my normal Wi-Fi. Are you able to still hear me?
Yes, sir. Continue.
Okay, great. Thank you. Okay. So we already talked about replicas, right? Disorder, but we had problem with breaking of the replica symmetry. So the big breakthrough Parisi had was to define as quantity. Okay, this don't worry about the mathematical detail. This quantity actually tells you how similar are these replicas to one another. So you can plot the values here. So for example, this value, this is called overlap. If it is 1, I just schematically drawn two replicas. This is replica alpha, this is replica beta. So you can see that these replica are exactly same, the same spins I have repeated, right? So these are exactly same replica, so they are similar replica. So the value in that case, their overlap is highest. This is 1. If the overlap is -1, then you can see that the spins are flipped over. So each of the spins, so here it's flipped to this one is flipped like that. Okay, these are anti-aligned. On the other hand, if Q is 0, then the two replicas are actually random. They don't have any correlation between them. So this is a big step that Parisi take. He could actually figure out how to compare different replicas, how to understand how similar are the replicas. That is one big step. And then he did lots of mathematics and then came up with this story. Okay, so the story is this: that suppose these are the replicas. There are many of these. I have shown only few of them. At high temperature, the replicas are mostly same, because, as I said, all the configurations have similar weights, right? The replicas are all same to one another at high temperature. So, so what you can do, so suppose you consider a particular overlap, okay, particular similarity between two replicas. So, for example, this value, for example, consider this 0.5 value. For example. So consider the two pairs. Consider these replicas in pairs. So suppose these two consider, and see the similarity. See whether it's 0.5 or not. If it is 0.5, then count 1 at this point. Then you go to another pair, for example, this one. See if it is 0.5 or not. If it is again 0.5, then again count 2. And like that. I mean, so you do a counting in this way, and then you do it for all possible values of Q. Then you will get such a curve, which is called the histogram or the probability distribution. So what is the probability that two pairs, one pair of replica will have an overlap of that value, and so on. Okay, so this is a plot that came out of the calculation of Parisi. Now, important point is that high temperature, such a plot will have only one peak. Okay, just one peak. Now, when you lower the temperature, Parisi's mathematics showed that these replicas, these systems, they are grouped together. Okay, so you can see that in this group, they are similar. These two replicas are same. Similarly, in this group, these replicas are same. But there is another group there where the replicas are same within themselves. And you can find such groups in huge numbers. The replicas grouped together. Second point is that the overlap between these, the similarity is very similar. So the replicas in a group, they are very similar to each other. And the system can make a transition from one configuration to another very easily. Okay, so although the transitions are easy, but the configurations are very similar, so you will not notice any change. The system is making those transitions, but because the configurations are same, so you would, nothing will be changed. Okay, that is one point. But if you look at different replicas from different groups, okay, they are very dissimilar. However, the dissimilarity also implied that the transition from here to there is very, very difficult. Okay, so this came out of the theory, and this actually explains now the frozenness of the spins. Okay, so if the spin, the system goes into that state, for example, then it cannot move to other state like this because it's very difficult to move. And it can move on within similar looking configurations, but then it will look the same, right? So that's why we see these spins to be frozen, and that's why it's also rigid, because it cannot move to other spin configurations. So this is quite stable. So you understand that, I mean, Parisi was able to explain most of the physics. So, I mean, probably most of you know in Nobel, I mean, so if we can win a Nobel only when your theory is actually experimentally proven. Okay, and turns out that this replica symmetry breaking, the signature that two peaks appear. So in this case, at low temperature, you'll see that there are multiple peaks that appear. At high temperature, there was only one peak. So this signature was experimentally captured. This is, I'm not going to detail of the experimental result, but this is a laser system, and they measured something which is mathematically very similar to the overlap of the thing. This is at high temperature. You can see only one peak. But if you lower the temperature at the lowest temperature, you can see that clearly there are two peaks appearing. So just like Parisi predicted. Okay. So these, apart from that, I mean, so the same explanation goes beyond. I mean, seemingly there was no order, right? So everything was random in the system, but there is a hidden structure in the replicas that Parisi found out. And these are the replicas, the dotted star replica, and they are grouped together like we have already discussed. Okay, but considering the overlap, they can be actually arranged in a tree-like structure. So in this, the distance between two replica, for example, this distance, okay, is like the dissimilarity between them. If the distance is high, they are more dissimilar. For example, alpha and beta are similar, they are close by, but alpha and gamma are dissimilar, or beta and gamma are dissimilar. Okay, so the distance between alpha and beta are sorry, I heard noise. Sorry. Yeah. So such a structure was there in the system, but it was actually you had to really dig deep using mathematical tools to find such a hidden structure. And this is structure, the tree-like structure is called ultrametricity. Now the implication of that is this. So why he won Nobel Prize? Because not only his solution provide this solution of symmetry, replica symmetry breaking, but it is a stunning array of extensions to a wide range of other systems, as noted by the Nobel Committee. And the systems are like what? So this same idea was used to solve problems in mathematics, biology, neuroscience, the brain-related work, even the computer science, machine learning. It's quite happening. It's a new thing. And so the people are still using it, and they have changed all these fields in a huge manner. Okay, so what are common in all these systems? They all have frustration that we discussed all at the beginning, and these are all examples of complex systems. Okay, what are complex systems? So they are systems where the overall behavior is not just the sum of those of the components. Okay, so for example, you just look at one component, you cannot actually predict the entire behavior. You have to look at everything together and what is the structure inside and all that. Okay, such a system is called complex system. Okay, and this is why Parisi was awarded the Nobel Prize, because his idea percolated to many other fields, and people are understanding those fields in a huge manner. Okay, just a connection with Parisi, connection made with Parisi. This is just out of my own interest I'm showing. So Parisi has recently moved to a new field. Okay, so which is the field where I work in. So if you look at this video, you can see that these are trees there, and these are actually birds. There are actually hundreds of thousands of birds, and they are moving randomly, but you can see that it's behaving like a liquid drop. And suddenly there are the high density region, and the high density region will kind of travel like a wave. Okay? These kind of fluctuations are happening at a length scale which is much, much larger than each bird length. And to understand such a system, it's a totally different mathematical framework that we use. And I am working in this field. Yeah, I am also working in this field, and I'm happy to see that Parisi recently had also offered his contribution to the same field. Turns out that some of the ideas he developed for spin classes are still working. Okay, so that's so amazing. Okay, so how much time do I have? So in the next part, I will be talking about the other half of the novel. So may I know how much time do I have?
So you can continue, sir.
Okay, then yeah. So then, talking about complex systems, I already told you that it is a system that has enormous number of components, and then you have to consider all the components together. Okay, overall behavior is not just a simple combination of individual behavior components. Okay, so most importantly, the thing that all of us know about complex systems is that they are chaotic, meaning that it's very difficult to predict anything. So a small deviation at the beginning might lead to very large deviation at the end. Okay, and of course, it is very interesting that it is also challenging that they are very difficult to describe mathematically. So one example, perhaps the most famous example of a complex system is weather. Okay, this is the most familiar example. All of us know that it's very difficult to predict weather. I mean, so in Tirupati, yesterday or even in the morning, it was weather was not so bad. I mean, right now, if you look outside, it's heavily kind of, it's over. It's like it's raining, and then there are strong winds, and it's fluctuating. And you never know if it is have a rain right now. You cannot predict that it will be still raining after 1 hour, right? So predictions are really hard. So this is a complex system, definitely. And the other half of the Nobel Prize went to these two gentlemen who worked on this system, weather and climate. And this is the connection. You saw that Paris's work ultimately lead to, was in a complex system, and the other half, the weather, is also a complex system. This is the interrelation. And the two gentlemen, they share the prize for the half of the Nobel Prize, is Manabe and Hasselmann. So Manabe is a meteorologist. That means that he's a scientist who studies weather and prediction of weather and so on. His education was in Japan mostly. But then at some point he moved to US, and then he, for most part of his career, he also worked on worked in US. And especially the Nobel work was done, I think, when he was in US. Currently, he is associated in all places like US and also in Japan. On the other hand, Hasselmann, he did his education, and also he is doing job mostly in Germany, in various places like Max Planck Society and Hamburg University, Göttingen University, from where he got the PhD. He works as an oceanographer and a climate scientist. Right now, he is also affiliated to institutes those are in US and UK and so on. Now, why they were given the Nobel Prize? So they were given the Nobel Prize for their pioneering work on developing climate models. Okay, for those who work on complex systems, this news came as a very happy news, because the word complex came in the context of Nobel for the first time, complex systems. Okay, so the whole community was quite rejoiced. But the fact that Manabe and Hasselmann got it, so that also raised some concerns. Okay, I'll tell you why. So first of all, let us see what is Manabe's contribution. So I'll just brush through it, okay, because I'm not exactly. Let us see how much I can explain. So there is something called a radiation balance phenomena. So this is our Earth's surface. This is atmosphere, and there is sun there. The sun rays are coming through the atmosphere and hits the ground, but the sun is at higher temperature, so the frequency of the sun rays are high. Okay, this light will be absorbed by the surface at a lower temperature, so the surface will again radiate back this light, but those will be low frequency, so we cannot see them. Okay, so the frequency is so low that that doesn't fall in the visible range. We cannot see them. But nevertheless, the rays will be radiated back into the atmosphere. Now, in the atmosphere, there are certain gases which are called greenhouse gases. Okay, so examples are carbon dioxide, water vapor. These are also greenhouse, and these are actually major players. Okay, these are the major greenhouse gases, carbon dioxide and water vapor. But there are other gases like methane, etc. So the rays that are incoming, these are high frequency, these cannot do anything to these gases. But the low frequency radiation that are radiated from the surface, they can be absorbed by these gases. They absorb and then they radiate back into the atmosphere. Okay, that hits up the atmosphere. And this process is called radiation balance. Part of the radiation that comes from the sun actually stays within the atmosphere, because the atmosphere maintains a certain temperature. And as you already can imagine, this is very important for all life. So without that temperature, no life can survive. This is very important. However, there is a danger as well. So if the temperature gets too high, then also the life cannot sustain. So people try to understand what is happening. I mean, so what is this explanation? Why radiation emitted from here is low frequency? So why these gases can absorb and radiate and so on? So the first efforts were quite long before Manabe. Actually, Fourier, I mean, so he did study centuries back. Okay, and he already found out that this greenhouse effect, this effect, by the way, the radiation balance, the effect that the radiation, all of the radiation cannot go out of the atmosphere, is called the greenhouse effect. That was found by Fourier. He was a French mathematician as well as physicist. He did it centuries back. Back then, he did not have a full understanding. So very recently, just before the 20th century, Arrhenius, another physicist, he found the physics behind it, physics behind the greenhouse effects. The physics, exactly the physics that I explained. The high temperature bodies will emit high frequency radiation. Low temperature bodies will emit low frequency radiation, and so on. This is the physics behind that, and that is actually understood by Arrhenius first. But after understanding that, he did some calculation, and he predicted that the level of carbon dioxide in our atmosphere, if that is halved, okay, so there was some amount of carbon dioxide in the atmosphere during Arrhenius' time, and he calculated that if the amount is halved, then the temperature will be reduced so much, because the greenhouse gases will be reducing, right? They cannot absorb they cannot keep the heat anymore. So the temperature of the atmosphere will reduce, but it will be reduced so much that there will be ices. Everywhere there will be ices. But on the other hand, if the carbon dioxide is doubled, the temperature will be increased by 5-6 degrees on an average, and that is a huge change actually. This is on an average, not on a day-to-day basis. Okay, so on an average, if the temperature increases by 5-6 degrees, that means that all of our land will actually mostly effectively go in underwater. Okay, this is a huge problem. We have to stop that. Okay, now these calculations were very, very primitive. Okay, very simplified, and this was Manabe's crucial contribution. So in 1965, he proposed a model which is actually very, very detailed. So what he did, he included the radiation that I already described, that was contained by Arrhenius, but he also included vertical transport of air mass. Okay, so suppose this area is heated up, then the air near that will also be heated up. So the hot air will flow upwards, right? As they flow upwards, they will also take the water vapor that is contained in them upwards, right? And on the upwards, the air might get cooled because the temperature is low, and then the cold air will come down. So there is a circulation of air here, and also circulation of moisture and other gases, right? So Manabe included that. Manabe included both the air circulation as well as the water circulation in this calculation, in this model, mathematically. He did it in a simplified 1D model, meaning that he just considered one column of this atmosphere, okay, and solved this system. This was the first model, the scientific first detailed model on this line. And with the calculation, he showed that the effect of the oxygen or nitrogen, they don't matter at all. What matters is the impact of carbon dioxide. The impact of carbon dioxide is huge. And he showed that if you double the carbon dioxide, then the average temperature of the atmosphere will increase by 2 degrees. Okay, that is slightly less than that is explained here. But the problem is that this is not out of danger, because this is just the average temperature. Manabe, in his work, he showed this curve. This is one of the most famous curve in weather science, by the way, that came from the Manabe's pioneering work. And you see what is there. I mean, so this is where Earth's surface is, okay, and this is the altitude as you go above into the atmosphere, and this is the temperature that is plotted. Okay, so here it's a high temperature. If you go up, then you see that you encounter low and low temperature and so on. So you see that the temperature is non-uniform. So although average temperature is going up by only 2 degrees, he showed that the temperature that is increasing in the surface of the Earth, that is huge. Okay, So, and that is what it matters. I mean, the temperature on the surface, if it increases, then it will also increase the sea level and also all that things, right? It affects the life on the earth. So he showed that this is actually alarming. I mean, the situation in our case is alarming. And he was the first to establish these facts that this is indeed happening because of the carbon dioxide and not because of the solar radiation or something. There's something has to do with carbon dioxide. Okay, not even say water. Water also contributes, but we cannot do much about water vapor. Okay, we cannot control that. But what we can control is carbon dioxide. That was the first implication that came out of Manabe's work. And you already, all of us will know how important is that to save our planet. So Manabe, after that, he proposed the 3D model. Okay, so he extended the 3D model from 1D model. And this is, again, the first of its kind. So this is the first 3D model of the atmosphere. Okay, that was Manabe's work. And then Hasselmann, contributed in another way. So he wanted to study climate. Okay, what is climate? So climate is actually averaged weather. So suppose this is weather that is plotted. Okay, so what we are plotting here? Suppose there is a temperature. This is temperature in a particular region. Okay, and this is time, inverse of time. You can imagine that it is also time. So from day to day, you can see that there are lots of fluctuations in the temperature. Okay, so couple of months back, the temperature in Tirupati was like 44 degrees, and now it's 25 degrees, around 20 degrees difference, right? So temperature fluctuates a lot from day to day. It also fluctuates like this. But if you average these fluctuations, you can see that there is a increasing trend here. Okay, so this trend is not the day-to-day trend. It's happening at the length scale of years, right? This is alarming. That means that this is called climate. Okay, the average increase in temperature is the change in climate. Okay, now how to study climate? Because things are so fluctuating, then how can you find anything meaningful out of it? So this is where Hasselmann actually took help from work from Einstein. So Einstein studied a very different system where you have very, very tiny particles, pollen grains, okay, very tiny particles suspended in water. If you look one of those particles, you will see that they are randomly moving along these red paths. They are all random, okay. But on an average, if you average those paths, you can see that there is a pattern. I mean, so this path, the black part, is the motion of the random particle. So the red part are like the weather, and the black part, the average, is like the climate. Okay, you can have a regular pattern. For example, here it's actually regularly decreasing and so on. So the equation to describe such a motion was derived by Lanzava and Einstein and so on. So this is that equation, where the small fluctuations are encoded in this time. Okay. Hasselmann showed that weather and climate can be exactly explained in the same manner. These fluctuations are the fluctuations like this, and those are included in this term. Okay, but by studying this, you can actually see how the climate is changing. This is the first ever firm scientific foundation of climate forecast. So before that, forecasting climate was very difficult, but now you can see forecasting climate was difficult because of these fluctuations. But you can see now that there is a clear trend, increasing trend, right? You have clearly forecasted. Okay, so another big, this is the last slide actually, another big contribution from Hasselmann. He could actually distinguish different factors affecting atmosphere. For example, if there is a volcano eruption at some location, that volcano eruption will actually increase that atmospheric temperature at that region. Okay, so that is a natural source, natural factor that we cannot do anything about. But there are factors that are human created. For example, the increase in carbon dioxide, we human are contributing a lot. Now, people who are debating, some people are saying that no, human factor is not important. Okay, so that is affecting the policymakers and things like that. And it is actually our whole future is dependent on that. And the debate was mostly because there was no scientific founding on this claim. Now, Klausmann, I mean, he was able to distinguish these factors and then clearly show with mathematics, okay, with clear foundations, this fact. Okay, I'll tell you what is this. This is observation of change in temperature, and this is year. And this black line you can see is the observation. Okay, this is on an average you can see that it's increasing. That is fine. But now the blue line is the change in temperature if you would consider only natural resources, for example, the volcanic eruptions and all that. Clearly, you can see that this is not the observed quantity. But then, if you include the human contribution as well as the natural contribution, then you get this effect. Okay, they exactly matches with the observation. This clearly shows that the human sources of climate change is really huge. Okay, and this is really the cause of concern. Both Manabe's and Hasselmann's contribution has led to big changes in policies taken up by different countries, and our entire world is kind of dependent on these observations. Okay, so this is why they're offered the other half of the prize, and this is where I end my talk. Okay, so I hope I could convey some overall messages. And I forgot to thank, but this is actually needless to say, I'm really grateful to the Regional Science Center in Tirupati for giving me the opportunity. Okay, thank you.
If any questions, then the audience may ask. They can type in the chat box.
Sir, I'll just, I would like to add something, like, based on the presentation that you have right now given.
Sure.
So the patterns of the birds that flying high in the sky that you mentioned, and then we are trying to kind of anticipate, like predict something based on that. We are trying to research as to what we can finally understand. Similarly, this organizational behavior of the ants, for that matter, the movement of the ants is also quite a complex system, isn't it, sir? Like, and
Right.
I believe that a lot of research must be happening even in this field.
Yeah, that's true. Actually, that's true. That's a nice question. Yes, yeah, that is true. There are experiments on ants. Okay, collection of ants, and there are various ways to do that. What you do, you take the ants out of their natural environment. Okay, collect them in a container, and they'll be like a fluid. Okay, but it's a very strange fluid. And you can also show that they have viscosity, they have elasticity and all that, but these are all the molecules of the fluid are all living beings. And so you have to study that in a very different way than you study a normal fluid. So you have to use the non-equilibrium statistical mechanics tools. Another way to study them is in their natural environment, like the birds are flying in their natural environment. You can also study ants in their natural environment. Things are a little bit different in case of ants, because here the birds are actually, they're seeing only a few of their neighbors, like 4 or 5 of them, and they're trying to align visually. In case of ants, there are chemical trails that each ant leave, and all the other ants, they follow the same chemical trail. Okay. However, along the trail, there are dynamics like traffic dynamics and other things that are very interesting to study. Yeah, I mean, yes, it's true that, I mean, even physicists, I mean, biologists are already studying them, but even physicists are studying these ant colonies.
Yes, sir. Yes. Thank you, sir.
Any question?
Yeah, I would like to mention that, I mean, if students or any other person have any further question that can come up later on as well. You are most welcome to contact me through email. So you can find my email in my website, and I start with the PH. Just feel free to contact me with any question.
So if no questions are there, and as sir told, later also you can mail or contact us, so that whatever the queries you have, that can be clarified or answered by sir. So with this wonderful lecture, we thank you, sir, for clearly elaborating the, of course, the topic is too difficult, but you have narrated it in a nice way by simplifying it, and maybe which is very understandable to all age levels. So thank you so much for honoring our invitation and giving this wonderful lecture today on the eve of International Science Center and Science Museum Day. Definitely in future also, if any requirement is there, definitely I will request you to extend your support.
Sure,
So
sure.
thank you very much, sir, and thank you one and all who have participated in this webinar. Thank you.
Thank you.